Hello students, this is Mr. Ezra, and today we are going to talk about absolute value functions. Think back to middle school when you first learned about absolute value, and remember that absolute value is the distance a number is from zero on the number line. It's always going to be a positive number or have a positive value because distance is a positive measure. So for example, the absolute value of positive 40 is positive 40 because 40 is to the right of 0, 40 units. The absolute value of negative 40 is also positive 40 because if you measure the distance from 0 to negative 40, it also has a positive distance of 40. And we indicate absolute value with these two kind of longer lines on the left and right side of the expression. Let's begin to talk about absolute value functions as a description of what they look like with their transformation. So when we get to the graphs of absolute value functions, you'll notice that they either look like a V with a line on the left and the right that extend forever up, or if it's reflected down, an upside down V where you have a line left and right that extends down forever. When we look at the function in function notation, we notice that the parts of the function tell us a little bit about what it's going to look like on the graph. So, for example, f of x equals a absolute value of x minus h into absolute value plus k. The a, the h, and the k tell us some things. First of all, the h and the k are where the vertex is. So this absolute value function is going to have a vertex, a spot where it changes direction. If it's going down, when it hits the vertex, it'll start to increase. If it's increasing, when it hits the vertex, it starts to decrease. The h and the k, since they describe the vertex, also tell us where that vertex shifts to from the origin, from 0, 0. So if there is a plus or minus inside the absolute value notation, then that would be a shift left or right. And if there is a plus or minus after the absolute value function notation at the end of the absolute value notation, then that would be a shift up or down. This a in the front, a times the absolute value, this a in the front, if it is negative, it indicates a reflection. Otherwise, it's going to indicate a stretch or a shrink, and we will notice this on some graphs in just a few minutes. So let's look at a few examples where all we have is the function notation and see if we can identify the transformations that are present. First, we have f of x equals the absolute value of x plus 1 into absolute value minus 3. The plus 1 here is inside the absolute value symbols, and you will note that like other functions that we've looked at, like quadratics and exponential functions and logarithmic functions, that this plus or minus inside the absolute value symbols is going to be the opposite direction of what it looks like, because in the base formula up here, it's minus h, and that minus sign is always going to change the value to the opposite. So this plus 1 is actually a shift to the left 1. But the minus 3 at the end doesn't have that limitation. It is exactly as you see it. So minus 3 is down 3. So we have left 1 and down 3. In example number 2, if you have a negative in the front of your absolute value notation, that's a reflection. And the plus 4 at the end is going to be a shift up 4 because it is outside of the absolute value bars. The third example has 3 transformations. We have an a, positive 2. It's bigger than 1, so it's going to be a stretch by a factor of 2. We also have minus 1 inside the absolute value bars. That's going to be a shift to the right 1. And the minus 6 at the end is going to be a shift down 6. All right, if you haven't been trying these along the way, try number 4 real quick in your head. See if you can get all 3 of the transformations. All right, so the 1/3, since it's less than 1, is going to be a shrink by a factor of 1/3. The plus 2 inside the absolute value bars is going to be left 2, shift left 2. And the plus 3 at the end after the absolute value bars is going to be a shift up 3 units. So hopefully you're finding this pretty easy, especially seeing as we've done lots of different transformations throughout the school year. And since you were in the ninth grade, we've done a ton of them. So maybe you are comfortable with this by now. It's not different than anything else that we've looked at. Let's talk about what they look like on the graph, and we'll use the vertex and the transformations in order to get our picture. So first, the vertex. Remember that comes from the H comes from the part inside, and the K comes from the part outside at the end. And the inside part is opposite, so the H is actually going to be +1 for the vertex. And the K is exactly what you see. It's going to keep its sign, so it's going to be -4. So our vertex is at 1, -4. So let's put a dot at 1, -4, way down here. Now, this is our vertex. Let's think about the transformations and what that means on the graph. All right, we have this 2 here, and that 2 in front is going to be a stretch by a factor of 2. We also have a shift right from inside here, shift right 1. And we already have shifted the vertex right 1 by knowing where the vertex was. And a shift down 4, we've already shifted it down 4. Now, the stretch is going to tell us the slope of the 2 lines that we're going to use to form our absolute value function. The slope is 2, or 2 over 1. So you can think of the slope as 2 over 1. That's 2 over 1. So we're going to go up to 1, 2 over 1. Up 2 over 1. And these functions are have a mirror image on both sides of the vertex. So on the left side, we're going to go up to left 1. Up to left 1. So we'll connect a line through these points on the left side and the right side of the vertex, and you should see a V. If you don't see a V, you are doing something wrong. All right, number 6. The vertex is going to be at, remember, look at this sign here and change it, -2, comma. This sign stays exactly the same for the K part. It's going to be +3, so -2, 3. And we can go ahead and put a point there. -2, up 1, 2, 3. Left 2, up 3. So there's our point. That's the vertex. All right. Now for the transformations, this H is also a transformation of a shift left 2. And this +3 at the end is a shift up 3. But we also have this negative at the beginning, and that transformation is going to be a reflection. So instead of going up and to the right for the slope on the right side of the vertex, we're going to go down. Think of it as having a negative slope. So this function on the right side of the vertex is going to have a slope of -1 because there's an understood invisible 1 here. And as a fraction, we would say -1 over 1. So we're going to come down 1, right 1, down 1, right 1, down 1, right 1. And we can see that the line that's going to form from this is going to have a slope of -1. On the left side, we're just going to go down and to the left. So it's the opposite mirror image. Down 1, left 1, down 1, left 1, down 1, left 1. And we'll get a line that goes, or a line segment that goes down through that as well. That is it. We've got our absolute value function upside down V because of the reflection. In this case, we're writing the equation given the graph. So you can pull the H and the K from the vertex. Where is the vertex on the first one? It is not left or right, but it is down 1, 2, 3. So we have a vertex of 0, -3. In the function itself, the absolute value bars are only going to have an x inside of them because we do not have a shift left or right. But there is going to be a -3 after the absolute value bars because there is a shift down 3. You can see that's because where the vertex is. Now, how do I find the number that goes in front, A? Well, first off, notice that the right side of the vertex is going uphill, so we know that A is positive. We know it's going to be a positive number. And to find it, we just have to find the slope of that line. So it is, if you find 2 good points that you can use to count to get the slope, we're going up 2 over 1, up 2 over 1, up 2 over 1. So the slope of that line is positive 2 over 1, which reduces to be just 2. Which means that the A part, the beginning part, is going to be a positive 2. In our second example here, our vertex is left 2, up 4, right here, negative 2, comma 4. In the absolute value bars, we're going to have x plus 2, because remember, it is the opposite of the sign in the h part of our vertex. But since the 4 for the y value or the k value is positive, we'll have plus 4 at the end. Now, notice that the right side of our vertex is going downhill. That means that our a is going to be negative, and we find the slope by just counting down and to the right, by finding the slope of that right side of the vertex. Down 1, right 2. Down 1, right 2 is a slope of negative 1 over 2, which is why a is going to be a shrink of 1/2, and the negative is the reflection that causes it to go down. So our final function is f of x equals negative 1/2 times the absolute value of x plus 2, close absolute value plus 4. Hope you're finding this to be pretty simple. Why don't you try a few and see if you can do it? Try these two, pause the video, restart it in just a second, and see if you got it right. Okay, in number 9, the vertex is 2, 2, which means that inside the absolute value, we're going to have minus 2 for the right 2, and plus 2 at the end for the up 2. When you look at the slope, it's up 1 over 1, up 1 over 1. Well, it is unnecessary to write a 1 in front of absolute value, just like it's unnecessary to write a 1 in front of a variable. It's understood to be there, so you don't need to put the 1 there. You can just write it as the absolute value of x minus 2 plus 2. For example 10, you should have noticed that it shifted left 1, down 3, which would be x plus 1 inside of the absolute value bars, and then minus 3 at the end. The slope of the right side of the vertex is down 1 over 2. So again, we have a slope of negative 1/2, and that is going to be your a before the absolute value. Let's talk about how to solve absolute value equations. So this is not graphing. This is something a little bit different. What we want to do here is we want to solve for x when we have absolute value of x minus 3 equals 6. Well, there are a few steps to do this. The first thing that you want to do is to isolate the absolute value first. That means that if there is anything else on the same side of the equal sign with your absolute value bars, you need to add, subtract, divide them to the other side of the equal sign, get rid of them. After you've isolated the absolute value bars on one side of the equal sign, then you're going to split the absolute value equation into two separate equations. Since what is inside the absolute value bars always comes out to be positive, whether or not the inside is positive or negative, we are going to split this equation, for example, in number 11, to be x minus 3 equals positive 6, because whatever x minus 3 is, if it were equal to positive 6, the absolute value of positive 6 is 6. Or we can have x minus 3 equals negative 6, because whatever this is, if it's equal to negative 6, the absolute value of negative 6 is positive 6, and that would also be true. So you're going to end up solving two different equations. In this case, to solve x minus 3 equals 6, I'm going to add 3 to get 9. To solve x minus 3 equals negative 6, I'm going to add 3 to get negative 3, because I'm going to add 3 to both sides. So I added 3 on the left and the right in order to solve both of these equations, and I got two solutions. I got a solution of 9, and I got a solution of negative 3. Now, the last step is to always check for extraneous solutions. And remember, these are solutions that algebraically work out. You've done the math, you know that you solved the equations correctly, you got your two answers, but you plug them back in and one of them or both of them do not work. You can do this in your head or in your calculator, but you should check your solutions always to make sure that they work. In this case, I'll check 9 minus 3 is 6, and the absolute value of 6 is 6. That works. Negative 3 minus 3 is negative 6. The absolute value of negative 6 is positive 6. So they both work. I know that both solutions are good. In our next example, number 12, we do not have anything outside the absolute value bars to worry about, so it is already isolated. We go ahead and split it into the two equations, 6x minus 3 equals 15, or 6x minus 3 equals negative 14, because 15 and negative 15, both absolute values of both of them is 15. I'll solve the equation on the left by adding 3 to both sides. After adding 3 to both sides, I will divide both sides by 6. 18 divided by 6 is 3. 3 is one of the solutions potentially. I'll do the same thing for 6x minus 3 equals negative 15. I'll add 3. Negative 15 plus 3 is negative 12. I'll divide both sides by 6. Negative 12 divided by 6 is negative 2. I need to test both of these in my equation, and when I plug both 3 and negative 2 in, they both work. So they are both solutions to this absolute value equation. Question number 13. In this case, the absolute value is not isolated, so we have to isolate first by adding 3 to both sides. 8 plus 3 is 11. Now that the absolute value is isolated on one side of the equal sign, now I split it into two equations. 2x plus 6 equals 11, and 2x plus 7 equals negative 11. So 2x plus 7 equals both positive and negative 11. I solve both of these. I'll start by subtracting 7 on both sides to get 4, and then dividing by 2. 4 divided by 2 is 2. And I'll do the same thing to the equation on the right. Subtract 7 to get negative 18. Divide by 2 to get negative 9. And I get two solutions. Now, both solutions are going to check out when you plug them back in, which means that 2 and negative 9 are both solutions to this equation. I would suggest that you pause the video, try a problem, see if you get it right, rather than just taking notes on what Mr. Esra gets. Whatever works for you, but that's a suggestion. It would be good for you to try a few of these before you get to your practice problem, so you know that you're whether or not you're understanding it or not. Number 14. The absolute value bars are already isolated on one side of the equal sign, so we have our two equations that we have to solve. 2x minus 5 equals both positive 9 or negative 9. I'll start with the positive 9 and solve that by adding 5 to both sides. 9 plus 5 is 14. Then dividing both sides by 2 to get 7. On the right side, I've got 2x minus 5 equals negative 9. I'll add 5 to both sides to get negative 4. Then divide both sides by 2 to get negative 2. When I plug in 7, 2 times 7, 14 minus 5 is positive 9. The absolute value of positive 9 is 9. Or when I plug in negative 2, 2 times negative 2 is negative 4. Negative 4 minus 5 is negative 9. And the absolute value of a negative 9 is positive 9. They both check out to be true. They both work, which means they are both solutions. I have a solution of both 7 and negative 2. Our final two examples today. 2x plus 5 equal 11, and 4x plus 10 in the absolute value bars equals 6x. They both have already the absolute value isolated, so we'll set up our two equations. Starting with number 15, that gives us 2x plus 5 equals positive or negative 11. I'll start solving both of these by subtracting 5. On the left here, 11 minus 5 is 6. Then I'll divide by 2 to get x by itself to get 3. For the one on the right, subtract 5. Negative 11 minus 5 is negative 16. Then divide both sides by 2 to get negative 8. When you plug in 3 2 times 3 plus 5 is 11. Absolute value of 11 is 11. 2 times negative 8 is negative 16, plus 5 is negative 11, which evaluates to be positive 11. Both of them check out, which means they are both solutions to the absolute value equation. Most of the time, I think that you are going to have two solutions. There are cases where you have one or zero solutions. Before I get to number 16, I want to try to give you an example of when you would not have a solution algebraically. So for example, if I had the absolute value of x minus 5 equals negative 6, when I start to solve this, I run into a problem because there is nothing that I can substitute for x that will give me a negative value. So because of that, this equation has no solution. I cannot take an absolute value of anything and get a negative response. So there are cases where there are no solutions. Number 16 is not one of those cases. Number 16 is going to solve to be something, but it is a little different in that you have a variable on the right side of your equal sign. We're still going to solve this in the same way by setting 4x plus 10 equal to both positive 6x and negative 6x. And as we solve this, we'll have to think about solving it a little differently. Since there are variables on both sides of the equal sign, we are going to have to collect our variable terms. That means that we want to get this positive 4x across the equal sign and collect it or combine it with the 6x on the other side. So I'm essentially going to subtract 4x on both sides so that I can get them together and get 2x. It is okay to subtract 6x to the left. There's no problem with that. That would just mean that you have to then subtract 10 to the right and then divide, so it adds an extra step in. But there's nothing mathematically or logically wrong with it. Once I have subtracted 4x on both sides, I'm going to divide both sides by 2. 10 divided by 2 is 5. So I get x equals 5 because I've got the x by itself now. That is a potential solution to this problem. I am going to do the same thing with 4x plus 10 equals negative 6x. I'm going to collect my variables to one side of the equal sign by subtracting 4x since it's positive here to get rid of it on the left. And then I'm going to divide both sides by the coefficient in front of the x, which is negative 10. So 10 divided by negative 10 is negative 1. When I test these solutions, I'll start by testing 5, and sometimes I just kind of come off to the side and do it in my head. So what is 4 times 5 plus 10? 4 times 5 is 20. 20 plus 10 is 30. 6 times 5 is also 30. So when I plugged in 5, it checked out. I then go back and look at it again, and I'll try the other possible solution by plugging in negative 1. Now remember, this is in absolute values. So that's 4 times negative 1 plus 10 in the absolute value equals 6 times negative 1. Well, I can go ahead and put all this together. 4 times negative 1 is negative 4. Negative 4 plus 10 is 6. But on the right side, 6 times negative 1 is negative 6, and I can't take an absolute value of a positive number to get a negative number, so it doesn't work. They're not equal to each other. It is what we call an extraneous solution. So this equation has only one solution, and that one solution is 5. I hope that you have understood this introduction to absolute value functions and some basic graphs with transformations and how to solve some simple absolute value equations. Absolute value functions are a type of piecewise function. In fact, they could be written as a piecewise function because the left side of the vertex behaves differently than the right side. So although I'm not writing these as piecewise functions today, you can make a connection to our last lesson on piecewise functions and see one in action. I hope that today's lesson has gelled with you, that it's made sense. Of course, as you're working, if you have questions, please do not hesitate to ask. I'll see you in class.